Now, so far, all we've dealt with is geometric moment of inertia. There is something you learned about in physics, mass moment of inertia. And its defining equation is this. The connection to geometric, the differential mass, dm here, is equal to the density times the thickness of a plate times dA. Total mass over area is density times thickness. Mass per volume is density. A times T is volume. So there's a connection between the mass moment of inertia and the geometric moment of inertia. In terms of volume, mass moment of inertia is given by the density times r squared dv about some axis, z in this case. Couple ways to integrate. This just illustrates you could look at an object like this. You could slice it up into disks and integrate up, or you can slice it up into cylinders and just integrate out. Those are just a couple illustrations of ways to approach integrating to find this stuff. Of course, a lot of the data is going to be in the handouts I gave you, in the back of your book, things like that. So, what is the mass moment of inertia about the z-axis? It should be mass divided by area times the geometric J naught of a circle. Should be the same thing. So we're going to look at it as integration by considering concentric cylinders, because in this case dm is going to be the density times the circumference of the circle dr. And I'm using capital R instead of little r in that they used. Density, and then I forgot one factor we got to have, h. So moving on. So here's our 2 pi rho h factor we got previously. RdR is dm. To get the differential for the moment of inertia, we got to multiply it by r squared. And then just do the whole integration and you get your answer. Now, to connect it up to, well, we got an expression in terms of density. Let's connect it to mass. Well, mass equals pi r squared. Now, you don't have to do the integral. We know the area of a circle. Pi r squared h, the height of the cylinder, area times the base, times the density. And just substitute. So here's pi, there's an r squared. And we can rewrite this pi r squared. There's the h. There's the density. So density h, pi. We'll just leave the pi alone. I'll just underline it like this to say we got pi. Now the r squared. We have r to the fourth here, so we'd have to have another r squared out here. And this right here is the mass. And we haven't got our factor of 2 yet. 1/2 m, what I circled, r squared. Now, we have sort of a cone. It's kind of a paraboloid cone type thing right here. And this equation y squared equals x defines the shape of the line that's making the cone. And so we're going to consider the disk. Well, we know the moment of inertia of the disk. 1/2 times, well, the mass in this case is the area of the disk, pi x squared. X squared is the radius now of the disk. Area times the height, dx. That gives you the volume of that little differential disk times rho. That's the moment of inertia of the disk. And we just add all the moments of inertia up. We integrate, in other words. dy, oh, excuse me. I got to change this to a dy, not dx. There we go. So, area, differential thickness, that's volume, times rho gives us differential mass. 1/2 mass times the radius squared. We have to have another factor of x squared over here. Okay, moving on to the next slide. Okay, so their DM is just like I came up with. They use that the disk is 1/2 mr squared, so that we get the differential inertia of the disk as we integrate upwards. I like to reason through these things on my own so that when I see it in the book, I go, oh yeah, it gives me practice, if you know what I mean. It gives you guys practice. Say, how would I approach this problem? Well, and then you see how they do it. So now we have the DIY, 1/2 x squared dm. I combined it all into one formula, which we came up with the same thing, the book and I. X equals y squared. So we could go, you have x to the 4th power. Well, dy, you could either substitute it this way. X to the 4th is y to the 8th. You could also do dy equals 1/2. Anyway, it would be complicated. This is the easiest way. So the parallel axis theorem for mass moment of inertia works the same way as what we learned before. In this time, instead of area, we have mass times the distance the mass is from the axis of rotation. So here's d right here. Radius of a gyration. If all the mass were concentrated at a particular radius, you get the same moment of inertia. There's that. Composite bodies. You find the moment of inertia of each part of the composite about the same axis. And then you can just add up the moments of inertia.